I'm going to speak about methods for assimilating observations of wind direction. And I'd like to acknowledge the small amount of funding that NSF has given me to pursue this research. So I'm going to talk about two-step methods, and two-step approaches to filtering go back to a paper by Jeff Anderson from 2003. In that paper, you have a two-step algorithm for implementing an ENKF, in the sense that the two-step algorithm is mathematically equivalent to a one-step ENKF. The nice thing about it, though, is it provides a different perspective, and both of the steps can be generalized away from linear Gaussian. So you can come up with algorithms for data assimilation that are not ENKFs. They're nonlinear and non-Gaussian. The question, though, one of the questions of interest here is, if you do that, if you come up with a nonlinear, non-Gaussian data assimilation algorithm, do you lose the connection to Bayesian data assimilation? Or if you don't lose it, well, what is that connection? I had a paper that came out last year where I explained what the connection is. You have to introduce a new random variable z that has the property that the probability of y given z and x is the same as the probability of y given only z. Extrapolating this notation backwards in time to Jeff's original paper, in that paper, he would have set z to be h of x, which is to say the observation, but without the addition of any kind of an error. You don't have to use z equals h of x in order to get a two-step method. All you need is this property here. Once you have defined a z that has this property, you can then write the Bayesian posterior PDF as an integral, and you can sample from that integral in two steps. First, you'd sample from the posterior distribution on z given y. That's like doing an update in observation space. And then you sample from the conditional distribution x given z. And in Jeff's original paper, that second step was accomplished using regression. But in order to make this connection between Bayesian data assimilation and a two-step framework, no assumptions of Gaussianity are necessary. So if you come up with a nonlinear, non-Gaussian step 1 or step 2, you don't lose the connection to Bayesian data assimilation, and this tells you what the connection is. In this paper, I applied some methods in this category of two-step methods to some example problems using Lorentz 96 and got promising results. I then wanted to extend this to a more realistic application, and I wanted something that could really benefit from this nonlinear, non-Gaussian approach. It reminded me of discussions that I'd had with Gil Campo, Philip Brohan, and Laura Slavinsky about the 20th century reanalysis, which they had worked on, and in general, historical reanalyses and the challenges associated with historical reanalysis. They specifically pointed me towards wind direction observations as a plentiful, relatively numerous kind of observation. There's relatively large number of these in the historical record, but which are difficult to assimilate using standard methods. And so the question is, how can you assimilate observations of wind direction? Well, it doesn't sound that hard on the surface, right? Wind direction is just a nonlinear observation operator applied to the state. If you have two components of wind, zonal and meridional, you just feed them into a nonlinear function and out pops an angle, and we know how to handle nonlinear observation operators, so what's the problem? Really, fundamentally, the problem is that the angle theta is periodic. So it's not a linear random variable, it's a circular random variable. It's not just that angles are bounded. So you could say the angle goes from minus pi to pi or something like that. We have ways of dealing with bounded variables. It's really the periodicity that's the problem. So for example, suppose that you have two ensemble members. Both of them have westerly winds, but one of them is slightly north of west and one of them is slightly south of west. If your angles run from minus pi to pi, and you just throw an ENKF at this problem, you'll find that the ensemble mean has an angle of 0, which is eastward, which is in the exact opposite direction from being correct. And you'll find that the spread is very large because both of the angles are very far from 0. So not only is it getting the mean exactly wrong, it's also getting the spread exactly wrong. This is just to illustrate why periodicity is really the fundamental problem here. In this talk, I'm going to develop two methods for assimilating wind directions. The first is going to be a genuinely nonlinear, non-Gaussian method that relies fundamentally on this two-step framework, the two-step approach. I appreciate, though, that not everybody has access to software that implements a two-step approach. The Dart software package does, but not everybody uses Dart. So I'm also going to develop an approximate approach that can be used with regular ENKFs and also with variational methods. So first I'm going to present the two-step method, and first I'm going to present the first step. So I have an observation of wind direction. I need to introduce a new random variable z. And sort of the standard approach would be to just say, well, z is the angle. I'm observing the angle, so let's let z be the angle. I'm not going to do that, though. I'm going to let z be the horizontal wind vector at the observation location. And I'm going to write it in polar form, so rho is the wind speed, theta is the wind direction. The first step, then, is to update the wind vector at the observation location, only at the observation location, using the observation of wind direction. I need to sample from this posterior on speed and direction. To do that, I'm going to make a simplifying assumption. I'm going to assume that in that forecast distribution, the wind speed and direction are independent of each other. You don't have to do this. There's nothing fundamental about this in terms of the two-step framework. But in terms of my algorithm, it is extremely convenient because it means that the observation of wind direction will only update the wind directions in the forecast. It will not update the wind speeds. So wind speeds stay the same and directions change. I need to sample new directions given the observation. I need to sample those from a Bayesian posterior. But now I have a scalar problem. Instead of having a two-dimensional problem, rho and theta, I only have a one-dimensional problem on theta. And I can use sort of standard ideas to do that. One of the standard ideas for this is to use a probability integral transform. That's the same idea that underlies Jeff Anderson's rank histogram filter. The details of my filter are quite different from the details of the rank histogram filter, but the ideas of both of these things go back to probability integral transforms. That's my first step. I'm not going to present any details besides the fact that I use a probability integral transform here. The details can be found in my preprint, which I'm happy to email to you if you have questions, and I'll put my contact information at the end. So that's the first step. You update only the angles in the wind at the location of the observation. The second step is to update all of the state variables based on the new wind vectors. And you do that I do that in exactly the same way that Jeff Anderson did with simple linear regression. There's one small difference, which is that in Jeff's paper, you have a scalar predictor variable. Z is just a scalar. So you have one predictor variable and a vector response. I have two predictor variables, U and V, both components of horizontal wind, but everything else is the same. So I won't dwell on it. So that's my two-step method. The approximate method, which is not a two-step method, is based on the following idea. Suppose you observe that the wind direction is northeast. That implies that the component of wind perpendicular to the observed direction, so the northwest component of wind, is 0. It's not an equivalence, though. If I say that the component of wind in the meridional direction is 0, that means that the wind could either be westward or eastward. If I say that the wind is eastward, it means that the north-south component has to be 0. So I'm I'm taking an easier or a subset of the observation information. The nice thing about this subset, though, is that it can be mapped onto the standard observation model. So I've observed theta sub O observed. And now to extract the component of wind that's perpendicular to that, I just take the dot product of the wind vector with this minus sine comma cosine vector. That is the component perpendicular, and I can set that equal to 0. But maybe not exactly equal to 0 because I'm not exactly certain about the wind direction, so I'm going to add an epsilon on there to indicate my uncertainty. And now, voila, I have an equation that maps onto the standard linear observation model. Y is 0, H is this vector, epsilon is the observation error. It's not exactly the same as the standard observation model, because in the standard observation model, the value of the observation is Y. Whereas here, the value of the observation is used to define H. So it's not the same, but you can still assimilate it in the same way. So with this observation model, this linear observation model, you can apply whatever variational method or ENKF you want. I do have a recipe for how to set the variance of the error in this model, but for the sake of time, I will not go into details on that. This schematic illustrates the two methods. I start with two wind vectors, the green and the red dots. The center of the figure is the origin. So the green dot is pointing just east of north, and the red dot is pointing just west of south. The solid line emanating in the northeast direction here is the observed wind direction, and the dotted lines that flank it represent the uncertainty in that observation. What the nonlinear non-Gaussian method does in the first step is it just rotates both of these wind vectors towards the observed direction. What the approximate model does is it projects these wind vectors so that they are close to being parallel to the observed direction. And you can see that the green dot is already in the forecast, it's already fairly close to the observed direction. So the two methods are not that different from each other. But the red dot is in the forecast, it's pointing in nearly the opposite direction. It's pointing in quite a wrong direction from the observations. So the projection approach is going to give you a fairly bad result in comparison to the nonlinear rotating approach. So this schematic suggests that if you somehow have already a relatively accurate forecast of the wind direction, and then you use the approximate model that I've described, your results should be pretty good. But if your forecast of the wind directions is all over the place, or if it's just quite wrong, and you apply this approximate observation model, then the results will not be good. So I test both of these methods in the context of a doubly periodic two-dimensional flow on a beta plane. So on the left is a snapshot of vorticity from this model. In the middle is a plot of the zonal mean zonal velocity. So you can see 3 eastward jets here, 2 westward jets, and then in the middle here, this is just a velocity close to 0 or maybe slightly westward. On the right, I have the kinetic energy spectrum. I'm forcing it in the shaded band of wave numbers. And so you have an inverse cascade of energy to the left to large scales and a forward cascade of entropy to the right to small scales. Within this model, I'm going to observe either geostrophic pressure or wind direction or both. And I'm going to apply both my two-step ensemble filter, or I'm going to use the approximate observation model within a standard ENKF. Here's a plot of results. So the left is the linear approximate observation model in an ENKF. On the right is the two-step ensemble filter. Both of these are showing time series of root mean squared error. The blue lines are what you get when you assimilate only pressure. And of course, they're the same in the left and the right because there's nothing nonlinear, non-Gaussian going on here for just an observation of pressure. The yellow lines are what you get when you only assimilate observations of wind direction. In the approximate model, you get nothing. This is just completely diverged. There's no benefit at all to observing wind direction with the linear approximate model if that's your only observation. Whereas with the two-step model, if you observe wind direction, the RMSE is as good as if you had only observed pressure, and that's a very promising result. It suggests that historical reanalyses, which currently use pressure observations, could get as much value by observing wind direction. And in many cases, you only have an observation of wind direction, not pressure. So this is promising. The red lines are what you get when you observe pressure and wind direction. So in the two-step version, you get some benefit by going from pressure only to pressure and direction. There's some improvement. Interestingly, with the linear approximate model, you also get a benefit by going from pressure only to pressure and wind. And what's happening here is that the pressure observations are giving you a forecast of the wind direction that is reasonably accurate. And then because it's reasonably accurate, the linear approximate model works. Whereas if you didn't have any pressure observations at all, the forecast of the wind directions is terrible, and the linear approximate model doesn't help you at all. So that's what's going on there. That's a summary of what I just described. The two papers are listed here. The discussion of wind direction specifically in the two-step framework is in a paper in TELUS that's in revision, and I'm happy to send you the preprint if you send me an email at ian.grooms@colorado.edu. Thank you for your time.